In this video, we'll continue our series on rate and equilibrium and how they relate to each other. And so we'll continue with the data we've acquired from our previous runs. We have our starting rate data. We then have our rate constants at 50 degrees Celsius calculated in our first video, as well as our rate constants we calculated at 25 degrees Celsius from our second video. We have the energy of activations, the delta H, and our KEQs from the first two videos. Here we're going to talk about what things have changed and what do not. How did doing this at two different temperatures affect things? For this, let's take a look at our K values. What we find is, as we got hotter, went from 25 to 50, our value increased from 0.001 to 0.015. And if we look at our K for reverse, 007 up to 019. As our temperature went up, our constants for the rate also increased. This makes sense. For the same amount of stuff, if your constant increases, you would have a faster rate. Rates generally go up as our temperature goes up. And so we expect a higher rate constant at higher temperatures. So usually a higher temp will mean a higher rate constant. Not every reaction is perfectly in line with this. There are exceptions, but this is a good general rule. We saw this for both the forward and the reverse reaction. What we didn't see was any change in our activation energies. They're not dependent on temperature. The activation energy is the hurdle that we have to go over. The two different rate constants at their different temperatures, what leads to the activation energies being obtained. When we look at our equilibrium constant, we actually see a similar change. Now, in this case, as we got hotter, our equilibrium constant got larger. This means we favor products. This may not always be the case. In this particular reaction, it was. What's going on? Why does this alter? Why is our equilibrium different? Both our forward and reverse reactions sped up. So why do we get any differences in our equilibrium? For that, we need to look at how much each direction changed by. If we were to look at the ratio of our rate constants at the high temp divided by the low temp, well, we could do that for the forward reaction. We'll see 0.015692 divided by 0.001001. If we calculate that out and just say, what's the ratio? How much bigger did our rate constant become? We'll find that our K forwards increased by 15.6 times. If we were to look at the same thing for our K reverse, 0.019284 divided by 0.007354, we'll find that difference is only 2.62 times. One of these had a greater increase than the other one. Well, if our rates have to be equal to be at equilibrium and the forward direction is moving 15 times faster at our higher temp, while our reverse is only moving 2.5 times faster, I'm going to have to build up way more of the product so that when the product multiplies by its K factor, it'll eventually equal the starting material times its K. What this means is that we are favoring going towards products as we get hotter, because the increase in the rates is not the same as our temp goes up. What this really means is that any time you have a reaction, if it's exothermic, or like in this case, if it's endo, what happens is that at high temperatures, we favor the high energy material. In an endothermic reaction, you need heat to go to the product. If there's more ambient energy from a higher temp, then we have more heat. We push towards that side. As an equilibrium argument, you can imagine heat being part of the balanced reaction. When we have an exothermic reaction, well, heat is a product. So as you build up more heat, you're going to favor going back to starting material. The higher your temp relative to some other measurement, the more you're going to favor the higher energy molecules. Why is this the case? Well, think about your particles. Remember, in any given material, you have a distribution of energies, which means if I have a bunch of starting material, many things have very little energy, few more have higher, few more have higher. For the reverse reaction, you have effectively the same distribution. It is much easier for something in the starting material to go over the hurdle because it has a much smaller hurdle in an exothermic. In an endothermic, this is the reverse. It's much harder to go forward. It's much easier to go reverse. More of the particles for the same distribution are able to get over that smaller activation energy, whichever side has the smaller activation energy. Well, this means you need less of the material before those rates are equal. And so we won't have equal amounts as is originally drawn. Instead, you'll lose a great deal of the material so that the total number of particles that are above the energy at any given moment is the same in both directions. You'll add more to the other side. So the total number going both directions will be identical. That's when our rates are equal, when the actual number crossing are equal. We think about this in terms of our graph over here. When our energy shifts as we get to a hotter distribution, we get more of our particles that are passed. If you were to compare that to the amount of particles prior to heating up, what we can see is that as we get hot, there's a much greater amount of particles that are now past that energy needed to cross the activation barrier. However, if you had a second energy of activation somewhere, well, that second activation energy, it had some amount originally. It now has an increased amount. But the relative ratio of the original versus the new amount is greater when you were further out in your initial activation energy than it is when your activation energy was smaller. The increase from the original green to the total green and red here is a greater ratio of increase than the original value here at cold temp in purple versus the total here at the hot temp in purple. This is proportional to what we were seeing up here when we were comparing these ratios. What's governing our rate constants? The amount of particles past the activation energy. Something with a larger activation energy being further out is going to see a larger ratio of increase with an increased temp than something that was much earlier in its energy, having already had a reasonably significant amount of the particles at that energy. And so because of that difference in the ratios that emerge as we change our temp, we actually see a difference in the balance point of how much material we need. So here's a thermodynamic component to balance out our kinetic argument for our equilibrium constants. Why does our equilibrium constant change as our temperature changes? Well, because our rate constants change, but our rate constants don't change by the same factor. Because of the difference in the energies of activation forward and reverse, the increase that we will see in particles able to go over that hurdle relative to what it was before the temperature change will be different for the forward and the reverse direction. The way this plays out is that at higher temperatures, it'll be easier to move to the higher energy material. At lower temperatures, it'll be easier to move to the lower energy material. and that is what we see in our equilibrium constants. Given that this is an endothermic reaction, at lower temps, we say a smaller K, we have less products. While our starting material in an endothermic reaction is the lower energy. And so at lower temps, we expect to go to the lower energy material. At higher temp, we expect to go to the higher energy material, which is our product, which means our K value should be larger as we have more product than we did at the colder temp. And so depending if it's an exothermic or endothermic reaction will determine whether your K gets larger or smaller with a temperature increase. The reason for it is the relative amount of the increase in our rate constants, based on the number of particles that have the energy to go over the activation energy forward versus activation energy reverse at the different temperatures.